I will talk about 19 minutes about best practices in non-invasive motor decoding for BCI control, at least at how we in Graz perceived that and how we developed over the last 20 years, kind of. And I want to show you some slides, some ideas of experimental paradigms. You may be aware of it, but since it's targeted to master students and early PhD students, so I think some of the basics are not too bad to bring here. So historically, in Graz, we started with BCIs in '91, not me personally, but Professor Furceller, and there was already this motor decoding idea somewhere there, so to have the connection from the brain to the spinal cord to the muscles, which is the normal pathways. But if this, why not reading the EEG, doing amplification and digitization, extra step at that time, and doing some neural networks, and to maybe control a robotic arm. Why not? Shouldn't this be possible? This is the first ideas to control a robotic arm or hand with a BCI. And to all do that, there was the basic idea was to use these sorts of imagining a movement as a first starter for a BCI system. A first online implementation was realized in '95, then later on. So this is more or less the topic we are talking about, at least I talk about here, in the general idea to use the intention of the patterns of movement, imagination or movement attempts, or for the control of a neuroprosthesis. We see this on the very left side there, on the right side for you, on to control a paralyzed limb again, for example. And how we can do this, there are several possibilities, and I just go into them very quickly in this next time. So we have, or I suggest there are 3 experimental strategies for this. And the first one, let's keep it very general, is the classical mental imagery. Whatever you want to control is completely independent from the task people look into. So any internal process which activates specific cortical areas. Maybe some of you know the cyclothlon, the BCI race. There people use different kind of mental activities to control the wheelchair on the track in that race here. Then we have more classical multi-imagery, so to imagine the movement, a hand movement of the right hand or of the left side, for example, and do this in a way so that really motor or sensory motor areas are activated. And finally, we moved over to, or left a bit the imagery side and suggest to, why not let people attempt a movement, so not to imagine it kinesthetically, which is a mental effort, but why not just try to attempt a single movement of a body part. So, 1 second here. So, I try to keep my computer running. So, let's go into this a bit. So, mental imagery, a classical paradigm. There are several papers about such things here. Available. And choosing any arbitrary task which helps people to bring different patterns which we can identify with the BCI. Multi-imagery is more classical, as I said, here also an old slide from us. So you see the activation patterns for a right hand, left hand, and foot imagination. What is always important that we always have the ipsilateral activation there, and this also can lead to some problems. Finally, when you find out that a person imagining left and right hand has very similar patterns, just little to distinguish, mainly in the ipsilateral side. So this but this is the beginning of all that, and a valid approach, of course, because there we know there is the area of the right hand, there's the area of the left hand. At that time, we were, of course, shy of thinking of single movements or attempting single movements, just repetitively imagine the hand movement and so on. so to understand the history a bit. So you know these videos maybe already. So a first attachment of the or connection between a brain-computer interface based on these very simple multi-imagery tasks, but arbitrary to the task itself, connected with a neuroprosthesis based on functional electrical stimulation. On the blue video right side is surface electrodes, on the other side here with an implanted freehand neuroprosthesis. So what we have here is, we used multi-imagery, however, for the upper video, foot movements, and for the other side, contralateral to the acting movement, so that we were not getting in conflict with the actual moving arm, at least what we thought at that time. Anyway, that's a long time ago. Let's go into more recent stuff where we said, we want to have more natural control and not this endless or this almost infinite exercise of the patients to imagine always the movements. It's really a burden, and the idea is I go first in this side here to detect movements, to look into whether it's possible to detect or to decode different movements from the same limb in a single trial basis. So we did several tasks here. One on the left side here is by Patrick. He sits over there somewhere, I think. He looked into different movements of the right arm, like opening, closing, rotation left and right, extension and flexion. Before we were not sure whether we can find differences. However, there is differences inside. And Andreas on the other side, here the video running, we looked into different grasps. Is it possible to detect or to decode different grasps, a pincer, palmar, and a key grasp? And we see mainly in the very slow components, low frequency range between 0.3 and 3 Hertz, that in these movement-related cortical potentials there are slight differences depending mainly on the number of joints involved. And this was quite interesting to see for us, and we used this finally to go into controlling a neuroprosthesis. Away to this, we see patterns from a spinal cord injured, here work from Patrick again, where we let people do a pronation, supination, open, palmar and lateral movement attempt, because we are here in a paralyzed world. And what we see is that you see nicely the colors, they are all differentiate a bit. What we learn is that especially the different joints, the number of joints is providing this information there. So when you compare pronation, supination is very similar signal, but compared to a lateral or a palmar grasp, it's completely different. And we can nicely also differentiate at least, so here for all 6 classes it's 45%, but in the 2 classes, when we look on the 2 classes only, we are up to 80% finally. So how this all reflect with patients, we have developed a screening here in that patient here, where he has to attempt movements, so hand open, 1 try only. Of course we don't see this here. He has to do a closing or a key grasp here, lateral grasp. He attempts it, we don't see it, and now a control movement, a rotation. And this is also here. We see also the movement of the patient so that we really see that the person is trying things, and we get these movement-related cortical potentials from that collections in a first glance, so with this abstract paradigm. However, in more grasp, this is the project we were going in developed a kind of a learning environment so that people can get closer towards the use of a neuroprosthesis. We see here another patient here. These patients are all tetraplegic patients with a complete lesion, Asia A, and a cervical level, in a neurological level of injury, C5. So what we see here is a more virtual paradigm, or virtual environment where the person see the soup with the spoon in there, and it indicated, of course, there must be a key grasp there done, so that the spoon can be grasped, and this is fed back. If it doesn't work, the hand makes a shaking movement. So we will see that did not work here. Next try a person is the BCI detects that movement, and the feedback shows what the first person view would see. The next thing is a rotation. We see also in the hand the person can do this, the rotation a bit, and the control here is a detection on this. So with this we moved forward to this kind of, here is a very, very preliminary thing where a person with, again, the third patient here with tetraplegia, the same level, can use a single movement attempt so that the fingers close with the neuroprosthesis. And what I also want to mention, also if you go further with patients' work, we need to get away with all the cables. So the only feedback system to the computer system inside is the smartwatch here, which shows the activity ongoing in the BCI. The rest is somewhere hidden in the backpack. And very nice is, of course, and this is also one of the learning things here, these movement-related cortical potentials need to be found in the asynchronous ongoing EEG. And that's the hard thing, the hard example here. So what is important to find a paradigm where you can collect many of the trials to train your classifiers to be then finally able to find these curves in the ongoing EEG and even differentiate then what it was an opening or closing and so on, so that you can really use it for control finally. That's still an issue where we and maybe many others also work on, I think. So discussion points from the classical multi-imagery and mental imagery, we go to the detailed movement. Here we classify mainly low-frequency EEG features, and the goal is to do this asynchronously. We, in our project, which ended many years back, and we had the crisis in between now, need to start again with end-user measurements here. The challenges still remain self-paced versus cue-based MRCPs. Cue-based, we have the cue, which makes another potential there, visual evoked potential is all overlapping. You all must just be clear what you're doing, and then you can find your way through the jungle of signals. And of course, we want to avoid false positives. I have some more slides and 3 more minutes. Of course, I don't talk about all this, but when we go to, and our goal is to make a full arm movement control, and one thing is the decoding of the trajectories, besides other things here, and I give you an example here. Is it possible to do this with EEG? We know all the examples from invasive BCIs, and we did our tour through that in the last couple of kind of 7 years. And one of the experiments there was a very simple experiment, but was quite nice outcome. We let people rotate the arm in a circle more or less, and recorded the EEG with 60 channels, but also the kinematics of that. And by applying some methods, Victoria will mention them later on, we were able to infer the trajectories from the EEGs only in the time domain on the left side, and with the regression method and with the Spock method on the right side, also in the frequency domain, in the most contributing frequencies. So it's possible in a circle, in a simple circle, to get this here back. We see the components reflected on the surface of the scalp also, and they are a bit different because the method is different. So one example I show you here is where we continued with that to a random movement. So people had to follow with their hand on that table. They followed, they controlled with their hand this robotic arm, the Chaco, and the idea was that the Chaco has to follow a snake on the screen. So we had nicely developed this snake so that it is decorrelated all directions and so on, so that people have to move around, and we recorded signals, we have the kinematics, and the idea is to train a classifier from the decoder, and then finally do online feedback. And there we slightly changed from 100% kinematic to 0% kinematic in steps. like described here. So every step we put more EEG, more noise into it, so to say, but informed noise hopefully into that, so that finally people were moving a lot. And we learned a lot of with this kind of things. So what we see, for example, you see the patterns is that the face is mainly correct, so the dotted is the correct movement, so the hand movement, and the blue and green lines are the two different methods to decode it from that movement. And what you see, the face is quite okay. What is not fitting at that time is the amplitude. And we found out that we need to put more information from the data in there. So people started to get larger and larger movements with the time. The less kinematic was involved, the more movements they did to get rid of that wrong amplitude with the incorporation of the distance and the speed. So the magnitude of velocity and position, we could get rid of this and had then equal sized amplitudes also. So here is a kind of one trial of that with including the distance and speed, and we see the person has to move the hand but is decoded to 100% from EEG, and the Jaco robot with the pencil follows or tries to follow the snake on the screen. So when we look at this now, what we also learned that these decoders don't work from the beginning. It always needs a kind of almost 10 seconds so that this goes in line. And then we can see how good such a decoder at the moment, as we can do it in Graz, follow that trajectory. We see the amplitudes are in the same area and the phases are correct in some time. So we have here an accuracy of about a correlation of about 0.3 to 0.4, where the random level is about 0.1. So we are far away from very good, but we are better than bad. That's good. It's EEG, guys. Yeah? No surgery involved. Yeah. So what we also thought, let's people train, and I come to a point I want to discuss with you. So we let people come in. This work from Hannah. I saw her already over there. People come and get a setup with all the 60 channels, artifact removal training, and so on and so forth. And they came 3 days within 5 days to go through that procedure, and they did the trajectory decoding, kind of, first the calibration every day, and then online trials and so on. A study which took about 4 hours for each participant. And we were hoping that we see some training effect, but we see no training effect. What we see, at least for the 3rd day, a demotivation effect, because the study is too long already. And this is something I also will discuss tomorrow in the non-invasive motor control workshop 1. Maybe we are coming to a barrier at the moment with this kind of paradigms. So I have some questions. What's about the real world? Yeah, I ask you. Are all these setups too complicated? So we we need to train eye artifact calibration, removal. We need to train decoders and so on and so forth. It takes a lot of time. Maybe source analysis can help here. Another student from Nitico is over there is working on this. Maybe we should include other rhythms. EEG people usually don't look so much into the gamma, but maybe we should look into gamma time to time. We take care about artifacts, just to make this clear. The whole arm control, yes, it's possible. We know that from Jen, from many other people using the UT array, maybe with ECOG. We see also first nice results in these days. We have first seen exoskeleton control by Benabid and colleagues some years ago, and some more is coming out. This is all possible. Is it possible to do this with EEG is my question. Yeah, I let this open to you to make your mind up yourself. And does this work with end users with high spinal cord injury? I did not show any data here for the trajectory decoding. We have one example, and it's on our YouTube channel also. This person with a C2 Asia A lesion has the same performance than healthy people do. So that's quite interesting that we have the same decoding accuracy here but for time reasons I need to stop here. And extensive user training, yes, we're working on that, how we can manage that without a big setup here. So that's from my side. Thanks to all my people in the lab, and if you have any questions, we have some more minutes time, 1 minute or so for a question.
Thank you very much. Thank you very much, Gernot. We have 1 minute for like 1 or 2 questions. Do you have any burning questions
afterwards
from the audience? Yes. I can try to bring a mic to you.
Thanks a lot for the presentation. You sort of talked about like moving from maybe active movement studies with healthy participants to motor imagery to motor intent. And I think what you're saying and what seems logical is that a paralyzed person would be doing like motor attempts. How well can ideas be translated between the different paradigms and like...
Excuse me, can you repeat that sentence?
So, if an end-user goal is to do motor attempt, but people come up with some ideas around motor imagery, or say, movement execution with healthy people, how well can you like translate ideas across those paradigms?
Yeah, so the translation between movement execution and movement attempt is there. I think this is the same thing, almost the same thing, because when we execute a movement, else able-bodied people we cannot attempt the movement, we execute it. And so this is the logical thing to do, I would say. Motor imagery is more an artificial task, which activates the motor areas, and for the beginning of the BCIs, I say this was the perfect thing to do, because it was the time for that. But I think with motor imagery, it will be very hard to control something, because it's a way too slow process. So we switch.
All right, I'm afraid we're going to have to move on. Gernot, thank you so much again. And of course, you'll be around, and you already announced the workshop, so I urge everybody to go check it out. I'm sure it's going to be very interesting. All right, then we move on with our next speaker, Victoria. So Victoria is from Argentina. She leads an applied computational neuroengineering lab, and she's going to be talking about invasive and non-invasive paradigms for motor decoding. And yeah, looking forward to it. Floor is yours.
Okay. Okay. Thank you very much. I will start saying it's a big honor to be here, like as the second track of this didactic session. And I'm going to talk about how we can use spatial filtering approaches for movement decoding, I would say in both, invasive and non-invasive BCI. So let's start with the following scenario. So let's going to think that we have a patient, and we are going to ask the patient either to perform motor imagery or motor attempt. And at the moment, we are going to use surface EEG. So we are going to have our electrical brain activity, and we want to transform this electrical brain activity into some control commands, right? Most probably to trigger an external device such as an exoskeleton, typical BCI for movement decoding. So the thing is that we know that we can decode movement by the contralateral side, right? Because we know that most probably the desynchronization events are going to happen in the contralateral side related to the movement. And if we focus in one of these channels at what is typically people was doing like maybe 15 years ago, it's like we see one of these channels, let's say C4, and we are going to see that there are some desynchronization happening and synchronization happening in the alpha and the beta band, mainly here in the surface EEG. So what is the more organic thing to do is to, okay, I'm going to take this electrode, and what I want is if I want to decode movement and I know that there is some beta activity or an alpha activity going on, I will do some, spectral transformation, and the idea will be I need to decode and detect this peak, right? So I have the movement, I have baseline, and I want to detect the movement itself. What we can do, easily people say, okay, I can just literally subtract what is going on in the surrounding of that channel, and this is what is known Laplacian reference scheme, right? And for that, we can see there that there is a bigger difference in between the peak amplitude that I have for movement with respect to baseline. And that will be, or that ideally will make everything easier in order to make the decoding. And other people say, okay, no, why don't we just subtract everything, every information that I have from that electrode? And that is called the common average reference, CAR. These two guys are reference schemes, but they are also spatial filtering approaches. Although the way everything is being there is not data-driven, it's fixed. But to be honest, we can do more. And the reason why we can do more is because we are using multi-channel data. So we have multivariate analysis here from a statistical point of view. And if we go a little bit farther here and we look a little bit deepened, what we have in every contact, in every sensor here, is actually a linear combination of different sources, of different statistical sources in the more general broadly area. So the idea is that if what I see in my computer, what I have been done with my amplifier system, right? What I see in my computer is a linear combination of sources. What I want is to estimate those sources. And I can estimate as many sources as channels I have. That is a limitation. So we don't know how many they are actually, but we can do that. That's the maximum amount. Another thing that we can do is to estimate different sources according to how we actually build this transformation matrix called here W, with the letter W, and at which every column of this matrix is what is called spatial filters. So we will be able here to then estimate different sources that will leave us to the opportunity to make some future learning, some re-referencing, and some denoising. For the focus of this talk, since we are here talking about movement coding, I'm going to just focus on future learning. So how is that we can use a spatial filtering approach, which means gathering all the information given by all the electrodes, all my recording together, in order to estimate some sources that are important, relevant for movement. And we can do that by our old great friend, common spatial pattern. This is a beautiful, I love it, this is a beautiful decoding method that can be used for decoding, but it's a spatial filtering method. So let's go back to our scenario in which we have these patients that we are trying to make some movement attempt on motor imagery, and we are using EEG. So here, for a synchronous BCI, we are going to ask the patient to attempt to make the movement. So we ended up having some trial that belongs to one class, movement, and some trial that belongs to another class, for example, rest. And since we know that the variance of a bandpass filter signal is equal to the band power, we know that, and we can prove that mathematically, we want to maximize, the idea of CSP is to maximize the variance of the spatial filter signal under one condition while we minimizing it to the other condition. And mathematically, really briefly, don't kill me, people, mathematicians, we can do this by just saying, okay, I'm going to have a set of trials that they belong to one class, and a set of another trial that they belong to another class. And please consider here, this trial has been bandpass filtered in a given relevant frequency band, right? So we want to extremize, we want to optimize. This is what we do with spatial filtering. We optimize some objective functions here, and this one is the one at which we maximize the variance metric for one class, while we minimize it for the other one. This is exactly what we're doing here. So the spatial filters are a new trajectory at which my signal will have this property. So this is solved by generalized eigenvalue decomposition, and in the end, what I'm going to have are eigenvalues. Eigenvalues that I can sort them, and at which I know the first one are the one that maximize the variance for one class, and the latest one are the one that maximize the variance for the other class. So I want to take my new directions will be the eigenvector associated to those eigenvalues. So I'm going to transform my data into that space. That is what we do. And we are going to use only the most relevant ones. That will be the first, these pairs of spatial filtering vectors that are associated to these eigenvalues. So as I start saying that the variance of the bandpass filter signal is equal to the power, in the end, what we take is the variance of these transformed signals. So what we do then, now we have a vector, most probably a low-dimensional vector, that we can use to train any machine learning classifier. but typically are linear classifier because we can have some linear transformation here and everything was beautiful. Well, so what we do here is both. We make some dimensionality reduction and a feature extraction. So we start from a huge, maybe high dimensional channel space, as many of you want, and we ended up having maybe 6, I don't know, features that were extracted for that information, which is great. So this is a basic, I'm going to say the gold standard like pipeline when we do movement decoding by using EEG. So we have our data, we want to filter it, and then we use CSP, for example, LDA as a linear classifier, and we have the output. And for those, I am an MNE user and lover. So for those that use MNE, you know that this can be easily done by 2 or 3 line of code. And something that can also be easily done by using MNE is that you are able to see these brain maps that are called topo maps, in which we can see how are the contributions of every channels to these particular, more relevant features that we were able to learn. These are called spatial parents maps, right? And this iteration pipeline has been improved, of course, for a lot of people, and we were one of those, and in which we can just, go a little bit further and say, I'm going to understand what is going on in different frequency bands and different temporal bands, and I'm going to apply CSP. This is a really old paper already, but we were able there to I want just to show you that the typical CSP can be really, really improved by using some just temporal and frequency band analysis. And also, this typical pipeline is also, we can use it, that we show that we can use this typical pipeline and apply some transfer learning approaches based here in optimal transfer from domain adaptation in this feature space, the CSP space, which is a space at which in the end, I learned my classifier. So we actually show how we can do that in the feature space by using optimal transfer for domain adaptation. And if you want to know more, please go and visit the poster 2C22. That is like a follow-up of this paper. But it's that important CSP that actually now there are also neural nets, implementations that try to, in a way, implement CSP by using these structures, these architectures. So this is one example, for example, of the paper that had been published 2 years ago. And if you want to know how to train deep nets for BCI decoding, chose pass-by for poster C321. But what about invasive recording? Can we use spatial filtering for invasive decoding? Well, it doesn't matter. It does matter which type of recording you're using. Here I'm going to talk about ECOG. I'm talking about local interpretation for subcortical areas, right? And let's think that we have a patient that has been implanted. What we want to do is to decode movement, and in particular, it's going to be a continuous movement, which is relevant, for example, for the treatment of Parkinson's disease. So again, we had electrical brain activity, we want to make some decoding, but what is different from before? From before, what we are actually having is a high spatial resolution signal. And that is one of the things that people just will say to me, while you're using spatial filtering, you have a really high spatial resolution signal. That makes no sense. And besides that, what we also have, differently from EEG, is that gamma activity is more like, we can capture gamma activity more easily. So we are going to get information of movement from alpha, beta, and also for gamma. And in gamma, what we see strongly is the synchronization events, not the desynchronization events. So this is, I would say, the mainly and roughly differences when we use invasive or non-invasive for movement decoding, and particularly when we think about invasive, and we think about why using spatial filtering, I will say something. Most of the paper in this area, and at least for Parkinson's disease, are using a single channel, right, for making decoding. But if you go a little bit closer and we go and see what is going on, although I'm using a super high dense electrogrid, what we are going to have is still a spatial filter approach. We still are going to have a brain recording as a linear combination of sources. I believe that. Because the balance conduction is still there. Every contact is not being, every contact that I have in my cortex is not that it's capturing only one sensor, only one, source of neurons that are firing together. Most probably it's a combination of them. So still, everything that I told you is still, valid. And let's think how we can use this in BASIC for future learning. So we have our patient, and we have asked the patient to try to make some force movement. So we want to decode this continuous target, right? And we're going to use something that is called source power co-modulation. That is like a casting of CSP for continuous decoding, right? So here, the main hypothesis of SPOC is a beautiful paper also for you to read, is that we want to find a special filter that extracts oscillatory signals whose power follows a given target variable. So we see there that the idea is that, the hypothesis is that there is one sources at which the envelope of that sources is really or highly correlated with my continuous target variable. And how can I do that? Is again optimizing some objective function, and here again we have covariant matrices for the same reason I said before. But the covariant matrices we have on the bottom part of this fraction is the one that measure this correlation or this strong covariance in between the target and the signals. And we show here in this publication of this year, how we can integrate this as an online pipeline, how we can use this for online decoding in the idea of improving adaptive deep brain stimulations. And this is a long paper story, but what I wanted for you to say is that we show how important it is to actually integrate all this information, or I would say gather all this information that is given by the multi-channel ECOG that's being used, as we show here that there is an improvement in decoding with respect to only using one channel. Importantly, as before, we are able to see the contribution of each sensor in the decoding performance by doing these spatial patterns topo maps. Okay, so this is the only thing we can do? No, this is not the only thing. So regardless of from where your data is coming, as long as you have local field potentials, okay, we can do not only feature learning, but also we can use referencing and we can do denoising. And there is a beautiful paper for invasive EEG that from Wojtek Lab that they show how we can use reference scheme from, for example, econ analysis. And also, if you want to know more, you can go to poster 1 if24, in which I present like a pipeline by using a spatial filtering approach to the noised acoustic vibration artifact that may have IEG data. But this is not the only thing. I mean, spatial filtering is a really active area, although it's been maybe quite a long time ago that is being used in BCI. And I'm pointing here and highlighting here some papers that I think are relevant for you to have. And to finalize this, I will say, and you may realize, I'm a fan of spatial filters. So I welcome you to this beautiful area, and I will say something. Once you wear the spatial filtering glasses, you are only able to see neurophysiology as a mixing up of some sources. So this is my lab in Argentina, and I'm really thankful for them. And okay, muchas gracias.
Yeah, great time. Thanks a lot. Wonderful talk. I was wondering if you have any questions. We have time for one or two. It was too mathy for most people. All right. Is there a question? Oh, yes. Thank you.
I guess I can just shout it out. I'm sorry if you covered this, but like, how do you deal with like multi-class with like CSP, for example, when you have more than one class that you want to do?
There are extensions for that. So CSP was built originally for binary. So I don't know if everyone had Kuskar. So how can I use CSP for multi-classes?
Yeah.
So originally CSP being thought, and it's actually the mathematical foundation there is for binary classification, but there are already some extensions for that. So you can literally like either contract like one versus everyone, and in the end what we do is after doing the optimization problem, You solely can analyze eigenvalue decomposition, easy peasy that. But the way you select which are the eigenvectors associated to the best, eigenvalues, you use, for example, mutual information, some, analysis of how to measure the differences across classes. So you do that. And M&E has the implementation of that. So yeah, you can also use it.
Wonderful. Do you have another question? Oh, yes.
Hi. Sorry, my question. Great presentation, by the way, and my question would be very vague. Since it's about EEG and the goal is to implement, anyone would see that EEG could be implemented in activities of daily life. Mm-hmm. So the goal would be to reduce the sensors, like the channels.
Exactly.
So for instance, if we are seeing motor imagery from two-channel perspective, which is like C3 and C4, or yes. C3, C4 and CZ.
Yes.
How do you think, what is the future of CSPs or spatial filters in terms of minimal channels?
Yeah, so the question will be can I use CSP although I have a low space channels, only 3 channels? I have used CSP, no CSP, but I have used all the spatial filtering approaches by only integrating 3 channels. For example, in this paper from the local film protection from the STN, this one, the STN data, so the subthalamic nucleus data, was only having 3 channels, and I was able to learn there. So the thing is that, of course, the more channel you have, what the theory says, the more channel you have, the better will be the spatial information you can have, and that's the reason why spatial filtering methods will improve to whatever a single channel will do. But there's no harm of using a spatial filterings when you have low counting of electrodes. In the worst case scenario, you will have the same performance as using either one of those channels. So use them.
Thank you so much for your insights.